So a bank is studying the time it takes 6 of its tellers to serve an average customer. Customers wait in line, then go to the next teller. The box plot for the last 140 customers and the times it took for each teller to the right complete parts A through C. So before I begin even looking at this Anova table, let's investigate the box plot. You will see when you are looking at research articles, when even you do your own research, that you need to provide some sort of visualization and or some descriptive statistics before we jump into any sort of inferential statistics. We need to kind of make sure that we can even run the inferential statistics. There are certain assumptions that we have to have. Randomization condition, independence condition. For the Anova, the variability needs to be roughly the same. And that's all sort of subject to interpretation. Yet we can see nothing here. There aren't any major departures from each other, as we've seen in maybe an earlier one in the homework. See, one little outlier here. Your iteration may have one or two. Well, here's another outlier down here. But we don't see just a slew of outliers on these plots. So the first question reads, what are the null and alternative hypotheses? So let's scan through here. We know it's not A. We know that the null hypothesis is that all of the means are equal to each other. So looks like B and E are my only two here where that shows up. And the alternative is that they are not. Not all the means are equal. So B is the only one that makes sense there. Okay. And if you notice, that's pretty much the null and alternative hypothesis for every Anova we'll do, right? So we have 6 different means. What do you conclude? And we're going to use a significance level of 0.01. So yours may be a little different based on the iteration that you get. So again, we're using a significance level of 0.01. So here's our p-value. So we didn't have to run anything. They ran everything for us here. And this is how a traditional Anova table looks. And so my brain, when it's looking at these, it almost always comes over here to the p-value, and then it'll glance over here at the f ratio. This is our test statistic, similar to the t statistic. So in this case, we have 0.0059. That's pretty low. So this is definitely lower. 0.0059 is definitely lower than 0.01, right? So it is low enough. We're going to reject HO. Would it be appropriate to run multiple comparison tests, like a Bonferrari test or something like that, to see which tellers differ from each other? So if we reject HO, so we're rejecting the fact that they're all equal. Well, we want to find out which ones, where is that difference? So it would be appropriate. So since the null hypothesis is rejected, it would be appropriate. Which one is that? A. Now, if we didn't reject it, then they're all equal, and there's no need to run multiple comparison tests to see which ones differ, because there is no difference. Hope that makes sense.